we can start, I guess.
Sure. But
Okay.
then you need to share the screen or do something.
Okay. I mean, I would like to use, if there are no objections, I would like to use Zoom's whiteboard, if it's okay.
Okay. Since I don't have a tablet now, I cannot even destroy your pictures even in the other mode also. So
yeah. Hopefully you can't. Yeah. So let me tell you about the games that we would like to study today. So they are called, I guess, Blackwell games. And so they are as follows. So we have an infinite tree like this. And, you know, it's infinite and every node has at least one child, we assume. But each node has only finitely many children. Only finitely many children. And so now what happens? So like the game on the first level,
so there are two participants, yeah?
Yeah, so there are two participants, we will, let's say, call them min and max. And so they gradually descend in the tree for infinitely many turns, but this kind of, so it's what they call it a simultaneous move game. Simultaneous move game. So this means that in every node, there is actually like, let's say in any node of the tree, there is actually like, there is kind of a matrix game. So, well, formally, this means that, let's say this is a node V, and there are, let's say, 3 children here, V1, V2, and V3. And in each node, each node is equipped with some set of pure strategies of min and some set of pure strategies of max. And these sets are finite. You can imagine this as if we just have a matrix, let's say 2 by 2 matrix. This means that, I don't know, let's say that max plays columns and min plays rows. And then and this represents, if this is a 2 by 2 matrix, this represents the fact that in this specific node, you have 2 possible what they say, as they say, pure strategies of min and 2 possible pure strategies of max. And if you play a pair of a min strategy and a max if you have a pair of pure strategies, this defines you the next node in your tree. So, and in this way, you can just imagine that this matrix is somehow filled with children of my current node V. So I don't know, something like this, maybe.
No, but I think it's easier to believe, and probably it will not make any problems, that in every vertex there are some two finite set of moves, and the number of children is the product of the number of moves for A and B, and they for min and max, and they have this.
Yeah. Okay. So you say that probably we can.
It's better to have 4 vertex just for simplicity.
But in this form, as Sasha said, I mean Kozachinsky Sasha said,
yeah,
VI's are real numbers, right?
No.
No.
Are just sums.
These are just nodes. This, I mean,
Okay.
what means that max plays second row, second column, and min plays first
okay.
row.
They play a small game to choose a next vertex.
Yeah. Yeah.
No, but it's just you can say they play to choose the vertex, or in more trivial thing that just their moves determine the vertex.
Okay.
Yeah, I mean, I would like
four
to stick
children
with
now.
this. Sorry?
There should be 4 children now. So you have 2 by 2 matrix.
No, I'm not insisting on it. I mean, I'm not insisting that I should have the number of children should be the product of the number of strategies of min and max. So, I mean, you can do this, but you can also consider games where 2 different pair of strategies may lead in the same
But
child.
Okay.
what I think is a bad idea is to use the name strategies, because strategies is something else in the game, not local things. So
I mean,
maybe to avoid confusion, it's better to avoid this name at least.
Or let's call them moves. So min choose a move, max chooses a move. They do that simultaneously.
And children
depending on the 2 moves they had chosen, we choose next.
According to some known rule, how it works. Okay.
yeah. And what we then we also have okay, so and the next idea is, of course, that we want to
What do we
consider-
maximize or minimize, you should say?
Okay, but, yeah, I mean, let's say this. We have some function, so I don't know. Let's say, so which assigns
A
infinite
real number to
branches.
any infinite sequence of vertices.
Yeah, let's say just a real number for a second. Yeah, so omega is the set of all infinite branches of my tree. So, okay. Yeah, that's now the next thing is that, well, if you have a game like this, we know that if you want something, let's say if we want to have, let's say we just have just one game of this form, we know that there might be no value of this game if we just consider, I mean, it just, you know, forget about infinitely many rounds, just one matrix game. Yeah, so, and then it consists of real numbers. We know that it should, in general, it doesn't have value, and in general, it doesn't have an equilibrium in pure strategies. So we have to consider a more general class of strategies. So let me just say what I want to, let me just finish what I want to say. I mean, we also assume that actually in each node, both players can use mixed strategies. So I don't know, let's say here min can choose the second row, the first row and the second row with probability 0, 1/2 and 1/2, and max can, let's say, choose the first column with probability, let's say 1.4, and the second column with probability 1.6. And then the next child is chosen at random according to these 2 mixed strategies. Let's say, what will be the probability that the next child here will be V2? Let's try to figure out. I guess, so what we
So it's,
I guess it's just 0.5, right? Because
yeah.
I go here, I have this with probability 0.5 times 0.4, and I have this with probability 0.5 times 0.6, right? So if I'm not wrong, this is 0.5, right?
Okay, so anyway, so for every vertex, the strategy for min is just a function that for every vertex gives the probabilities. And the strategy for max is the same function for his code moves. And then a probabilistic process appears, then they make this choice independently in each vertex, and then we get a distribution path. Yeah?
Yeah.
That's what
Yeah.
you say.
Yeah, so exactly. So the strategy of min, exactly. So in every node, I fix some distribution over moves of min in this node, and similarly for max. And then if I have two strategies, let's say sigma of max, global strategies, right? And tau of min. So my global strategies are consist of local strategies for every node of the tree. The local strategies, are these probability distributions of the moves of the corresponding player. And then I have, if I have a pair of strategies, then this gives me, probability distribution on the set of all infinite branches of my tree, right? In the usual way. So it gives me like a randomized process of producing an infinite branch in my tree. Then what I'm interested in as a result of two strategies, we are interested in the expected value of my function that one guy wants to maximize and one wants to minimize, right? On this probability distribution. I don't know, let's for short write it as follows.
So we assume that the function is somehow Borel and bounded, so it always exists, or what?
Yeah, we assume that f, for simplicity, we assume that f is from 0 to 1 and is Borel.
So the pre-measure of every interval is a Borel set, so it's measurable.
Yeah, with respect
so it's integrable.
To product topology on this omega.
And then you claim that this game has an equilibrium.
Yeah, I mean, I claim that. Yeah, I might say I claim that it even has a value. I mean, what I want to say. I mean that there exists the theorem of Martin is that in such games, for every such game, well, there exists some number x star such that if I, on one hand, if I take any number which is smaller than, let's say, for any x which is smaller than x star, there exists a strategy of max such that so it guarantees that the outcome, that the outcome of a play on average against any strategy of mean is at most x. So it guarantees that for any strategy of mean, it is at least
At
x.
least x. No, so
sorry.
anyway, you don't claim that there are optimal strategies which guarantee something, or at least x or at most x for max and mean.
There are,
but there are some kind of approximation things.
Yeah, there are almost optimal strategies.
There is some threshold, and below the threshold, max can get whatever, get as close to the threshold as she wants, and above the threshold, min can get as small as she wants.
Yeah. So let me just finish writing down the theorem. Strategy tau of mean such that so, and for any indeed for any number above the threshold, there exists a strategy of mean which guarantees that the average outcome of a game of this strategy with any strategy of max doesn't exceed x, this number below above the threshold.
So Bruno, is it clear now? Or
for me it's clear. And so the first question
it's
So can you prove this by looking at the finite part of the tree at finite? So you cut off the tree at finite depth?
No, for example, imagine that one of them wants to get a non-periodic sequence and other wants to get a periodic sequence. So on the finite depth, you don't have anything reasonable.
What you say? Yes, it's Borel measurable.
More than, it's just sigma 2 or something like this. Yeah, okay, maybe if it is so clear that you maybe can even say this in Russian or not.
I can say it in Russian.
Yeah, just if it's very clear, it's just perfectly clear something, if you can explain this in Russian. No? Not that?
Есть стратегия. Каждый...
Okay, let's make a simple thing. You probably can understand this in Russian. So, если надо ли объяснять, в чем состоит теорема еще раз, или всем понятно, в чем состоит игра и в чем состоит утверждение?
Теорема Мартина, в смысле?
Ну вот эта теорема, которую Саша предлагает доказывать.
Да.
Ну и то, что вам-то понятно,
я извиняюсь. Да, я имею в виду, что действительно вопрос про эту теорему.
Да. Что, народ, скажите, понятно, нет?
Формулировка понятна.
Да.
Вроде понятно. В формулировке два строгих неравенства. Если их заменить на нестрогие, то теорема перестанет быть верной?
Да.
Если заменить на нестрогие, это значит просто заменить на равенство.
Ну, в общем, для x со звездой непонятно, что происходит.
Да.
Понятно.
То есть, вообще можно сказать так, что игра очень простая, даже первый нетривиальный случай, что два человека пишут 0, 0 или единицу независимо друг от друга. Написали на доске и показали друг другу. Потом они еще раз пишут, еще раз пишут, еще раз пишут. Потом приходит арбитр, бесконечный момент, приходит арбитр и говорит, сколько первый должен заплатить второму. И вот утверждается, что у такой игры есть справедливая цена, что, значит, вот есть какие-то способы, значит, есть какое-то число, и больше этого первый всегда может избежать среднего, в среднем избежать, а меньше наоборот. Okay, and maybe now you can give an example which shows that this is important, this more complicated things is important, so there are no strategies that would guarantee just at least x star and at most x star.
Yeah, I can. I mean, at least for one player.
Yeah. Why cannot we replace this like Kola says, why cannot we replace strict inequalities but non-strict inequality?
Yeah, let me try to do so. Let's just so the game, let's say we will have a game on a finite graph, but it will be possible to formalize it as a game on a tree of this kind. So let's just consider the following game. We have I don't know, something like this. We have 3, I don't know, nodes, something. And
so first we explain game in terms of the graph, and then we translate in the form we need. So what is this game?
Yeah, I mean the game, you start in node V.
Yeah.
And there are 2 players, and let's say whenever they are and let's say that they have the following matrix here. Okay, let me just write it down. So I have here S V V T. So I mean we start here, and the goal of Max, let's say, will be to reach S. The goal of Max is to reach S. And so what happens here? We start here, and so Max have 2 pure moves, as we call them, and Min has 2 pure moves. And so they play them, possibly they may use mixed local strategies. And I don't know. So if the result is S, you come to S, and let's say the game is finished and Max won. So formally, like you can say that our function here is 1.
And in T is 0 then.
Yeah, and for T is 0. And so you see that, and if you stay forever in V, then Max also loses. It's also
0.
Our function is also 0. So you can just write it down as a tree, like if we start with V, it has 3 children V, S, and T. But if you ever come to S or to T, then everything like is already determined. Here we have 1s on every infinite branch, and here we have 0s on infinite branch. And then there is also one infinite branch that consists only of V's, and here you have 0. So I don't know, is the game clear?
Yes.
It's not clear why you need to complicate the things. Just let me say something simple and you tell me whether it's correct or not. Imagine there is one player.
Yeah.
And and he produces 0s and 1s.
Mm-hmm.
And the referee comes and counts the number of initial 0s.
Yeah.
If it's infinite, if it's only 0s, you lose.
Yeah.
But if it's finite, you also lose. But the more 0s you have, you not so seriously lose, but also lose a bit. And the more 0s you have, the smaller you lose. So if you have 0 and 1, if you have n 0s and then 1,
so if you have infinitely many 0s, right?
you lose 1.
Let's say I don't know, the outcome is 0, right? If you only 0s. Right?
Okay, yeah, and if you have 0 and n 0s and then 1, the outcome is 1 minus 1 over n.
1 minus 1 over n.
No, just forget the case when n is 0, but n plus 2 to make things easier.
Yeah.
1 over n plus 2. Напишите там.
1 over n plus 2.
No, 1 minus, no. 1 minus 1 divided by n plus 2. I just don't want to n be in the denominator be 0, just to avoid troubles.
Okay. Anyway, yeah.
So it's somehow it's profitable to postpone your 1, but if you postpone it indefinitely, then you lose a lot.
Ну и чему равно x звездочкой?
1. So you cannot reach 1, but you can reach as close as 1 as you want. So this effect doesn't depend even on the two-player game. It's just and mixed strategies or whatever, or non-full information. You just have this problem with already with games with one player. Yeah. Sasha, say something.
Yeah, I guess so. I mean, if you use probabilistic strategies, then this doesn't help.
No, but what can you do if you use?
Yeah, I guess this shows that you can. Yeah, so your example is better.
No, but if your example illustrates something interesting, it may be still worth trying to consider it, but then you should explain what it illustrates.
Okay.
Or just give it as an exercise. So,
okay, I mean, this example, I mean, this is like a reachability game. So, okay, I mean, we can analyze it. And so you see, the game of this form. And I'm claiming that Max, whose goal is to reach T, has, so X star here is 1, but Max cannot reach it. And to get arbitrarily close, to get arbitrarily close to 1,
yeah,
you just have to play 1 minus epsilon here. I mean, you always choose this thing with probability 1 minus epsilon, and here with some small but positive probability also.
But I'm confused. So your game is almost symmetric, just Max has a small disadvantage. How can the value...
No, it's not symmetric because Max loses if, so we have an outcome that the game always stays NP.
If Max has disadvantage, then the value should be smaller than 1/2.
No, Max has advantage because you can just with high probability.
I think Bruno is right.
Huh?
So the game is almost symmetrical, but Max has some small disadvantage here. How it can be close to 1? No, it's impossible.
Okay, maybe you should make it like this. Yeah, I guess so. Yeah, I mean, anyway, we can go on if so. We got previous example. But I think if it's like this, then yeah, then Max has now then it's not symmetric, right? Yeah, it should be like this, I guess.
Now it's even more symmetric than before, I guess.
No, because now you have
S is a good vertex for
yeah. S
it appears 2 times in the matrix.
Yeah, so now if indeed, so yeah, sorry. So if I use 1 minus epsilon and epsilon here, well, why cannot just I can't just always choose the first column? What's the problem?
Because if the opponent will always choose the second, then you will stay infinitely in the vertex, and you get.
So Max chooses a column.
Yeah, Max chooses a column. And so, but why we can get arbitrarily close to 1 anyway? Because if I reserve some epsilon for here, first of all, I mean, with probability 1, I will at some point I will go somewhere to S or to T, right? Whatever mean place against this strategy, right?
Yes.
So I just have to consider this moment, and I just have to show that when we leave B, the probability of going to S is much bigger than to T, the conditional probability, right? And you know that's clear because whatever we have, whatever mean place here, mixed strategy P and Q, I don't know if P is greater than 0, then probability of going to S because of this is 1 minus epsilon P, and here is just epsilon P. So it's much greater than this, and we can also have here probability, right? And then if P is 0, then anyway you go to S for sure. Yeah. So, yeah, so I guess, okay, maybe let's proceed to a proof of this theorem.
Yeah. And so you know the proof of the theorem, and you will tell us the proof modular determinacy theorem for Borel games, yeah?
Yeah, so, I mean, let's then just recall. So we will show that there's Martin theorem 1. Or let's say there is one theorem, Martin-Borel determinacy theorem, and what I want to show is that this theorem implies this Blackwell determinacy theorem.
Извините, я в самом начале должен был спросить, Blackwell это такая фамилия? It's just a name, or it's a word which has a meaning?
As well as Borel.
Okay.
Well, I mean, as far as I know, okay. And so,
but he was later than Borel, I guess. He's quite recent. At least I think.
I guess. But anyway, let's just recall Borel determinacy theorem. And the difference here is that we also play on infinite trees. But the first difference is that it's alternating move game. So we assume that, let's say, on the first level, let's say in the root, when one of the player makes a move, then on the second level, well, you know, on even levels, one of the player makes a move. On odd levels, the other player makes a move. And the theorem is that, and then all infinite branches are split into two sets. One is winning for one player, and the complement of this set is winning for the other player. And the claim is that one of the players always has a winning strategy as long as omega is borrowed.
Yeah. So I looked, but meanwhile I looked about Blackwell. So he proved the theorem in 1969 for G delta games. And this was before Martin, I guess. And then Martin came.
What is G delta?
No, it's not just a Borel set, but a set of the second level of the Borel hierarchy.
Ah, okay, yeah. All right. Yeah,
And
but then Martin came and simplified his proof to improve.
Extended his proof for
Yeah.
yeah.
So, you know, that's not just some random guy. He's good. Yeah. Anyway,
Martin is not a random guy, definitely.
yeah, and Blackwell turns out.
And Blackwell.
Because, you know, for second Borel hierarchy, it's also like it's already.
Блэквелла есть еще это самое, какие-то результаты вовковской науки, предсказания с экспертами, там есть условия Блэквелла, при которых там все хорошо.
There are also some other results related to predictions with expert or whatever. But anyway, this let's go.
So the theorem states for this game. So and they are just deterministic, and they are just 0, 1. So you know there is a winning set, not like a payoff function. And it states that one of the players has a winning strategy. And important difference here, and that will be useful for us, is that there may be infinitely many children of any node in the graph. So, and in general, it may have arbitrary cardinality. The degree of R3 may have arbitrary cardinality. And in Blackwell games, we have only finitely many children in every node, because otherwise, you know, just you know, one-shot matrix games, von Neumann games, or how we call it, may have no
If you allow infinitely many children, then it is not clear what means Borel set.
Why
So
not? I mean, you just
No, it's bare 3. Why not?
so
You have countably many children.
I'm just consider the product topology. Yeah, I mean, I just consider as basic option sets as usually all sets that are continuation.
So the set of moves is topological space.
Yeah.
No.
No.
It's a bare space. What is the problem? It's just a space of all sequences of natural numbers. What is the problem with that?
Because Sasha said that can be not only naturals, but any set, even uncountable. Sasha.
Yeah.
Then you have discrete topology on this.
Yeah, I have discrete topology on. I don't know if I have an arbitrary set A, and then I consider infinite sequences of elements of A, then I can consider, like, how they call it, product of, no, I mean, just as basic open sets, I can consider all sets that have, I fix some prefix, and then I consider all possible continuations. And then if it's Borel with respect to this topology, then it has a winning. Then then it's determined, as Martin showed. So okay. I mean, I have to ask. So now, is it clear from what theorem we are trying to derive our theorem?
Вроде ясно.
Okay.
Понятно, в чем состоит теорема детерминированности борелевских игр, или надо еще что-нибудь сказать? Народ. Ау.
Вроде это та же теорема.
Вроде понятно, да.
И раньше.
Да. Нет, а что-то граждане молчат? Ну ладно.
Okay.
So
infinitely many children is a bit fake for me and the strange topology, but we only apply Borel with finitely many children, and then everything is
but
fine
in our
for
applications, we will have to use this theorem for trees with infinitely many
But even uncountably many.
Uncountably.
Oh.
It's just will be like the set of probability distributions or something like this.
Yeah. No,
Yeah.
it's cheating. No.
Why?
Maybe next time you will give the proof of Borel determinacy theorem.
I mean, in Borel determinacy theorem, you also have to consider inevitably you cannot just prove it for finitely many children. And,
okay, then you will inevitably consider this next time. But now we accept that for a while that we have
you should
infinitely
accept
many.
everything because you have no other options. Okay, and then
So we have infinitely many children, but the topology is just it's a metric space. The metric space is the same. The distance between two paths is determined by the place when they diverge. So
yeah, I mean, I guess, but I will not have to use any metrics, but I just need topology.
But so it's not a problem of what is a Borel set is.
A Borel set? What are open sets?
No, just standard intervals, because it's a metric space, and you if you take a path and
you mean you are asking what is the Borel what is the topology if there are infinitely many children? Yeah, so that's the question.
No, I'm not asking anything. I just saying to comfort the people that you can consider as a standard metric space when the distance between two paths is 2 to the minus n if they diverge at nth level. And as in any metric space, you can define open sets and Borel sets and this and that. So no problem.
But topology is defined.
And topology is defined by the interval.
Without metric.
Without metrics.
Okay. On the slides there is how to say base of open sets.
Yeah, base open set for a topology. But if people think that this is somehow difficult and metric space are better, they can also believe in this.
Okay. Yeah, okay. Anyway, let's try to proceed, I guess. So there will be two steps. So first of all, let me give like a general scheme. So I will define, I don't know, something which I will call X certificates for mean. And the first step will
be, X is what, number?
X is, yeah, it's from 0 to 1. And the first step will be to show if there exists X certificate for mean, then mean has a strategy guaranteeing that the average outcome, well, you know, guaranteeing that it's at most, guaranteeing that the average outcome is at most X. And on this first step, we will not use the magic will happen on the second. I mean, in the first step, the Borel determinacy theorem will not be used. It will be used on the second step when I will show that if there is no X certificate for mean, then Max will have a strategy guaranteeing that X minus epsilon for every epsilon. I mean, for every epsilon, Max has a strategy guaranteeing X minus epsilon. And I guess it should be clear that with these two things, we didn't define what a certificate is, but if we show these two things, then we will be done.
So I have two complaints.
Yeah.
First complaint is you have X certificate for mean, and then you should have Y certificate for max, just for symmetry. Why
Yeah,
don't you have them?
Yeah, we will have. Yeah, we will show that. Kind of show also that Max has a strategy through a certificate.
This is first complaint. And second complaint is that for a game in one round, you still have to prove something like Neumann-Morgenstern theorem.
I mean, of course, I assume this. Yeah.
So you will not prove it in a new way, but you just want to use the result as a black box.
Yeah.
Like Borel, you want to marry Borel, Martin with Neumann, and you both use them as a black box. Да?
Yeah, sure, yeah. I mean, I guess there many people here can just prove it, know how to prove it, but you know, I guess. Okay, so yeah, I'm surely using the theorem that, you know, started.
Sasha, it's not clear. X certificate in this definition, X is a real number, right?
Yeah, it's a number from 0 to 1.
What is the assumption of step 1? There is X such that there is a certificate, or what?
No. Step for every X.
Yeah, for every X, if there exists an X certificate, you know, as long as you provide me, so now X certificate, it's like X is the quality of a certificate. And as long as you provide me a certificate with quality X, then min has a strategy. You can convert it into a strategy of min. And as long as you cannot do this, then you can use this fact to show that Max has a strategy, guaranteeing not X, but maybe a little bit smaller.
So if you have, I don't know, 1/2 certificate, then you have 1/3, 2/3 certificates, yeah?
Yeah. Okay, so let me just show what it is. What is a certificate for me? It's a simple thing. It's just a certificate or a
Сейчас, Саш, давайте я вам расскажу неправильное доказательство, видимо.
Да.
Объяснить, что там не так.
Okay.
Ну, давайте будем рассматривать просто все действительные числа и для каждого из них применять эту теорему. Для игры такой, что min выигрывает, если выигрыш, значит, если результат меньше, либо равен, скажем, x, а иначе выигрывает max.
Если
Значит,
результат. Подождите, то есть игра будет либо выигрыш, либо проигрыш.
Да, либо выигрыш, либо, ну, как в первой теореме, как в теореме Мартина первой.
Да.
Значит, понятно, что это будет борелевская игра, потому что f борелевская функция. Правильно?
Да.
Ну, значит, будет у нас у одного из двух игроков выигрышная стратегия.
Okay. No. Since you are speaking in Russian, this is a kind of violation of the rules, but it's accepted because your argument is completely nonsense. So you do not lose anything. Of course, you consider games with independent moves or games with full information. If you want games with full information, then we have Borel theorem, Borel determinacy. But for games with independent moves, we don't have any result. Even if the outcome is 0 or 1, it doesn't change anything.
And also, like, I don't understand you're saying that. So you kind of turn all outcomes where the pair function is smaller than x to 0, and all outcomes that
No, I said that I consider some game where exactly one of the players wins. Like in the
But the game is with full information or what? Not with full information.
I'm sorry. I see now why it's nonsense what I've said. Because I haven't proved that this we can apply the first Martin theorem to this game. Because this is not a game with full information, right? I'm sorry.
Yeah. Okay, so let me try to say what the NX certificate is. It's just formula is just a function. It's just an assign. We just assign to every node some number.
So you explain what is a certificate.
Yeah. I'm explaining. Yeah. So it's just it's just an assignment. It's just a function from the set of the nodes of my tree to 0 to 1. But it has to satisfy some restrictions. The first restriction is it's kind of local. Okay, let me try to. So let's say I have somewhere. So for every node, V of my tree, I should have the following. Let's say, so this is my node V, and again, let's say it has 3 children. I just don't want, let's consider on an example, I don't know. And let's say we have some matrix like this. So again, like V1, V2, V3, V1. And then I consider the game where I substitute each. So then I consider the game, which will be just a game matrix filled with real numbers. So I substitute V1 by C of V1, so by the number assigned to V1. And similarly for all the other nodes. And then this is just a matrix with numbers from 0 to 1, and it has the value, right? And my restriction is that the value, so my certificate should assign to V some number which is at least as large as the value of this game, which is obtained by replacing children here by the numbers assigned to these children by my certificate.
So Min has a strategy guaranteeing him less than C of V.
At most C of V, to be precise. Yeah.
So is it clear or not? So let me say again that for Min has a certificate, he has some plan. Plan is just what he will have at every level. So for every vertex, he has some function. And what we require that locally, this function is consistent. So if we consider the values of the function as a result of a game at every level, then Min has a strategy which guarantees something better than current value.
Yeah.
Kind of an upper bound of what Min can achieve somehow.
Why better? Worse?
No, Min.
Like the idea is that if we came to V, then we can play in a way that
the outcome is at most
C of V.
So since we are Min, we want to guarantee upper bounds for our outcomes. So if now we have bound V, C of V, it should be, we can guarantee something by playing Nash equilibrium, not Nash, at Neumann equilibrium, we can guarantee something better than...
But from Min point of view, if you take upper bound, it's worse than exact value.
Okay, yeah. So what we can achieve is better, that is promised. C of V is a kind of a promise. And the value of this matrix is the actual what can be achieved.
I see.
So we can achieve better than we promised.
Yeah.
to
So
achieve.
yeah. So the idea is that we kind of in V we can achieve, assuming that, for example, for some reason we have shown that in V1 we can achieve at most C of V1. In V2 we can guarantee, guarantee at most C of V2, and in V3 we can guarantee at most C of V3. Then we can then this implies that in V we can guarantee at most C of V by applying here the optimal strategy of mean, right?
So imagine, in other words, imagine we have some kind of static evaluation of position. So mean has some decide that in position in vertex, in node V, his evaluation is C of V. And this static evaluation should be consistent. If static evaluation of something is small, then it can be achieved if the game is extended by one step, and then the static evaluation is used. No?
So if we set a C equal to the constant 1, then the first condition is satisfied.
Yeah, exactly. But then it's bad because
There will be
the root
condition.
will be assigned to 1, and you just guarantee that everything is at most 1.
No, but look, if C is 0, constant 0, then it also can be guaranteed. I don't understand then the problem.
Okay, then we have to remember, we have to state the next condition, which
now the final
says
function
something about the payoff function.
Not anyhow involved in this.
Yeah. So, and the second condition involves, it says that for any infinite branch, if I have infinite branch like this, then the value of my payoff function on this infinite branch should be at most, let's say, lim_inf of. So I take the value of my certificate along these branches, along my branch. I take lim_inf of these quantities, and this lim_inf should be an upper bound for f. For any
But why lim_inf, not lim_sup, not lim something else?
No, it will be not important. It will not be important, because we will use a theorem that martingales have a limit with probability 1, and then everything. It will not. It will not matter.
Okay, you say that if your static valuations are good, then the actual outcome is also good.
Yeah. So I mean, so is it clear what is a certificate? And X certificate, X is just the value of the root. So like the quality of the certificate is its value in the root. So, okay, and then the claim is that if we have a certificate like this, and let's say me takes, in every node, just some optimal local strategy with respect to C. Well, with respect to this matrix. Then this global strategy guarantees that the average outcome is at most C of the root. So this is our claim, and it proves the first step. right?
But it's quite unobvious because the certificates are saying something along a path, and then we need to compute an average, and it's not obvious, and lim-infs should be somehow used. And
okay, let's try to show then this.
Сейчас понятно, что происходит, или непонятно? Is it clear or not now?
It is.
So I will try to prove it here. Proof of the claim. So okay, so I take any strategy of max which tries to place against this strategy of min, which plays optimally everywhere with respect to C. And then I obtain some probabilistic process, right? I mean, and then what I would like to look at, I just look, let's say, I will have some sequence of random variables. This C0.
Wait a bit. So you consider deterministic strategy for max or probabilistic strategy?
Probabilistic.
For finite games, it was the same, but for infinite, it is probably not.
I mean, I just consider any strategy. It doesn't matter, the argument. I mean, yeah, I cannot, let's say, can I just say that global strategies of max somehow the weighted sums of global deterministic?
Not really. Imagine that max, that min,
I'm not sure, but
no, imagine that max wants to get so and they make at each step they make bit 0 or 1, and then they take XOR, and then max wants that this XOR of the sequences has limit frequency 1/2.
sort
And
of
if he
like
plays
any
randomly, he guarantees this with probability 1.
prefix.
But for every deterministic strategy, he doesn't guarantee anything.
You mean you take the XOR, so they play like what?
No, one produce x0, x1, x2, and then another produce y0, y1, y2. And then the referee comes and computes x0 XOR y0.
So you mean just you have not infinitely many rounds, just 6 rounds, right? Or what?
No. I thought about infinitely many rounds.
Okay. Then why you have 6 or what?
No, not 6. No. So one produces x0, x1, x2, x3, and so on.
Yeah.
And another.
So you mean simultaneously, right?
Simultaneously, x1, y1.
Okay. Yeah. Sorry.
And then a referee computes the XOR of them and checks whether the XOR has limit frequency 1/2.
Yeah.
And so it's obvious probabilistic winning strategy for max, who wants it to be 1/2, is to use random string sequence.
But let's say, no. You are saying that we first fix some strategy of one of the players.
Okay, no. Maybe this also happens on the finite level, so it's nonsense what I'm saying. Yeah.
I mean, anyway, for the argument, it doesn't matter, so I can try to
Okay,
fix it.
sorry. Mixing things, yeah.
Yeah, so I can consider that the counter strategy of max is also like probabilistic. And then I will look, then they play, and then I can look let's say, what will be the value of my certificate on the 0 level? Well, but then it's fixed. It's not interesting. But then C1 already can be, it's not fixed. It's
so then if you fix a strategy, so we have a fixed strategy for min, which is optimal strategy on every level, and we consider any probabilistic strategy for max.
Yeah.
Then the game is well defined in the sense that at every vertex we have some conditional result, if with average conditional result, if we start from this vertex.
Yeah.
And you want to compare this result with the certificate, yeah?
Yeah. I mean, well, I don't know. So what I want to do is that just I know what we can understand is that for any I, the expected value of this thing is at most C of the root. Right?
Yeah, but to prove it, you need to make it by somehow by induction. So you need for every vertex the conditional expected value starting from this vertex.
Yeah, I mean, what I know
less than
that
C of
I
this
have, so I have fixed two strategies of max, and then at every node V, I just have a probability distribution on its children, right?
Yeah, and you want to claim that this is smaller than the certificate.
And yeah. And then what I know, since min uses the optimal strategy, then this thing.
But what's the definition of CIs?
So I have fixed two strategies of max and min, and then they randomly produce an infinite tree, an infinite branch in my tree.
Mm-hmm.
By playing in each current node two local strategies that we fixed. So C1, for example, will be the value. So I take the node into which I come on the first after the root, on the first, and I take the value of the certificate of this node.
So
just imagine. So we have
CI is certificate of the ith node.
Yeah.
When they play according
CI
to these
is
strategies.
C of VI, where VI is also random variable, which is, and then I have. So my infinite tree will be formally like an infinite sequence of these capital VIs, right? So, and you can imagine that these things are defined just as, so what just happens is that, let me try to say what just happens. We have an infinite trees, and its nodes are labeled by some numbers from 0 to 1. I mean, every node is labeled by some numbers, by some number. Let's say C of, I don't know, 0.5 or something. And then what happens is that you fix two strategies, and then you can imagine that you have a probability measure on the tree, right? So in every node, you have conditional probabilities from some node V to come into the next node. You have P1 for V1, you have P2 for V2, and you have P3 for V3. Then what happens is that you just come, you descend in this tree like as a probabilistic, and when you came into V, then you choose your next node, you sample V1, V2, V3 with probability P1, P2, P3.
So you want to say that C is a super martingale with respect to this common measure, yeah?
Yeah. So I want to observe that C of B must be at most, at least C of B1 times P1 plus C of B2 times P2 plus C of B3 times P3. So we have to understand it somehow. Well, the reason is that we had a condition like this, that CV is at least the value of, this game. The game where if you have of this form. And then mean uses the some optimal strategy with respect to this matrix game. It means, but then what will be, and we also fixed some strategy of max. And when we fix these two strategies, then we have that we come into V1 with probability P1, into V2 with probability P2, and into V3 with probability P3. Then this means that if we have these two local strategies, then the average outcome in this game is this thing. But on the other hand, since mean uses an optimal strategy, then this outcome doesn't exceed the value of this game, right? Because mean uses an optimal strategy, which guarantees that the outcome is at most the value. And C of B is at least the value just by the requirements of the definition of a certificate. So, I mean, this was long explanations. Why this holds? I don't know. Is it somehow clear?
I think it is.
Yeah,
Okay.
for me it's also clear. But then the problem, you take lim_inf, and so you need to integrate over lim_inf somehow. And why is it not a problem?
Then it's not a problem because the sequence CI has a limit with probability 1. So there exists some, I don't know, random variable x, such that x with probability 1, we have that x equals limit of CI.
So you claim that martingale convergence theorem is also true for super martingales.
Yeah, sure. I mean, how do you prove it? I guess, first of all, I guess I mean, what's the difference? You first show that. So yeah, so I'm relying on the theorem that they like call it dupe theorem, that super martingales have a limit with probability 1. No, and you show it like this. If you just show that super martingale is bounded with probability 1, and then you show and then you transform any martingale which is into the other martingale such that if the initial martingale didn't have a limit, then the resulting martingale
Hello?
has. Yes.
Somehow I'm. No, maybe you can decrease it or increase it to get.
So I guess something wrong with me. Please, can anybody tell whether you hear me or not?
We can hear you.
Yes, right.
Okay, yeah, okay, sorry.
So I think there is some problem with Andrei.
And Sasha maybe.
And Sasha. Oh, so yeah, we lost friends.
Something
French
happened
pie.
in French. I
Right.
don't know. I hope that's not like.
Oh yeah, they disappeared. Both. Right.
In France. So, I mean, so, yeah, so I rely on this theorem that the super martingale has a limit with probability when 1, and then I just say what? Then I just say that first of all, by my condition, I have that limit of my CIs is at least F just everywhere, right? And then I'm
Sasha,
saying,
what is W here?
it's just the infinite branch that we have as a result of our random process. So we have an infinite sequence of.
So it's by the second condition. So C of I is just C of VI.
Yeah.
And by the second condition, we have this inequality.
Yeah, exactly.
On the other hand, it is a small C of the root because the expectation is.
On the other hand, so first of all, this thing, we know that it has a limit with probability 1. Then I just can write that it's almost everywhere, or like almost sure it just equals to the limit of these things, right? So I mean, let's say let's say it more correctly. So we have that there is some random variable x which equals to the limit of CI, such that so we know that with probability 1 there exists a limit of CIs, and we let the random variable x be this limit. And we define it arbitrarily elsewhere where this limit doesn't exist. So I know that so this random variable x, except for the measure 0, equals to the limit of my CIs.
But write probably x of w as you write in the right hand side.
Yeah, x of w. And in particular, this means that
Да, тут у нас все прорвалось, я прошу прощения. Sorry for.
Yeah, I mean, I was explaining why you can, assuming that we have this result that like super martingale has a limit except for the set of measure 0, how you derive our what we want from here. So I mean, I was saying that then so then I let so then I define then I can just say that, let me say it again, then that lim of Ci just equals lim of Ci with almost surely.
Yeah.
And then I just I'm saying okay, so then I'm saying that
you use something like bounded convergence theorem for Lebesgue.
yeah, so I just want to write that then so if my sequence of random variables converges to some other random variable with almost surely, so then we also have that the expectation of
And expectation are
Ci
always
converges to the expectation of my random variable x just as numbers.
And expectation
like,
on finite levels are guaranteed by this martingale property that they don't they don't exceed C.
yeah, the fact that there is some random variable x such that this sequence of Ci's converges to it almost surely on a set of probably of measure 1. It's guaranteed by the theorem that you know, by this, so there is a theorem of this form for super martingales.
It's monotone convergence theorem, I guess.
It's not monotone.
The
so
Ci,
you need bounded convergence.
when I increases, then expected value of Ci decreases.
But monotone convergence is,
yeah,
it's not expected values. It should, all the values should increase and decrease.
I mean, you're saying here, or you mean here
sorry,
or here?
it's bounded convergence. Okay, I
remember. So it's bounded convergence. Yeah, I mean, you first say if you converge to something almost surely, then you converge in probability, meaning that if you consider all the points where Ci
it's very
differs
clear
by
on
x.
Wikipedia.
Yeah, I mean, yeah. So, and then you just have to observe that this thing is always smaller than C of the root. So it, you know, the expected value of Ci can only decrease. And then the x coincides with lim almost everywhere. And then the expected value of x is at most just equals the expected value of lim, and lim is just a pointwise greater than or equal to f.
And all Ci's are at most C. Expectation of all Ci's.
Their expectations are at most C. Yeah.
Boom, 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 boom.
I mean, I can even try to explain why there's no difference. To show why the limit exists, right? I mean, first of all, you have to
you already explained why the limit exists. It's convergence theorem, martingale convergence theorem.
Okay, yeah.
But there is super martingale converge. We need super martingale convergence.
But it's the same proof, just with inequalities everywhere.
Yeah. I mean,
Okay,
you just imagine that.
Some more meditation is needed to understand this for me, but
you play on the stock market while some thief steals money from you. So if you oscillate even while somebody steals money, then you're a very rare event.
We can prove this convergence by playing sell high and buy low strategy. Yeah. But if somebody steals money, this is not so obvious that the strategy works. So for me, it's kind of things which I need to think about. But Sasha, you claim that there is no problem here.
Yeah, I mean, I see no problem. If you know that you infinitely many times your money are below 0.9 and infinitely many times above, I mean, you don't have to imagine that. I think it's not good to say that somebody steals your money. It's better to say that you yourself give away your money. Some amount of your money just.
But if I'm forced to give
you just you spend some of your money and the rest you used to play on a stock market. Imagine like this.
I'm sorry. This discussion about convergence is very interesting, but is it needed? Suppose we define a random variable x as lim_inf of Ci. Then, as I understand, expectations of Ci is not converged to expectation of x, but can be bounded. We need only inequality.
You want to derive from the fact that expected value of lim_inf of something is at least, I don't know what you would like. I guess we would need the following thing, that lim_inf of the expectations is at least than the expectation of the lim_inf.
Yes.
And then
is it wrong? It seems that it should be true.
No. No, in one direction. No, it should be there's something which is called lemma fatu, but is it in this direction or in another direction?
We need only one direction. We need inequality.
Yeah, of course, but
I mean, you can also try to show something even stronger, right? Because we know that every E of Ci is at most our x, which is C of the root, right?
Mm-hmm.
So it will be sufficient to just show that, I don't know, lim_sup of the expectations is at least expected value of the lim_inf. Maybe, I don't know.
No, we need no, it's not the direction we need, because imagine that every Ci has every Ci has average one half, but somehow lim_inf of these functions, the function is 0 on half of the space, so lim_inf will be 0, and
yes, and the inequality holds.
No, but we need another inequality. We need greater than f of w.
Why? We need inequality which is written on the board.
No, but
because we have a global inequality. Expectation of Ci is upper bounded by.
Oh, so you have lim_inf here, yeah.
In this direction, it should be true.
Yeah, I mean, maybe.
To me, it's more reliable than convergence for supermarket games.
No, but But then this works either for lim_inf or for lim_sup in the definition, but maybe indeed it works for lim_inf. But so maybe you use the weak version of criterion when you assume that something is smaller than lim_inf. But in fact, with martingale convergence, you can replace this lim_inf for by lim_sup and get a stronger result. But maybe you don't need the stronger result, and so you don't need martingale convergence, and it's enough to have this.
But the point is that anyway, in step 2, probably we will have to use the other direction of this inequality.
For martingale convergence, we need.
I guess, because we definitely, I guess we don't have here equality, right? Because if we have just a limit, then we have equality, right? Because that's the whole thing. So we don't have to think. If we know that the limit exists, then you can replace limit and the expectation. Well, under some. If everything is bounded and converges with probability 1. Yeah, probably at some point of this theorem, you don't even have to think about martingales, but I'm not sure that you can avoid using this theorem everywhere in the proof.
Yes, we have step 2, and maybe in step 2 we need convergence.
Yeah, in step 2 we need to, well, the idea is that we have to, we have to lower bound this thing, because we will be playing for Max. We will analyze things for Max, who wants to show that the average come is at least something. So we will have to show that this is at least something, and we will want to use like similar arguments, and you can replace expectation and limit. But I guess you cannot just say that limit of the expectation just equals expectation of the limit.
No, I think it's not true. Sasha provided an example.
Yeah. So I guess the example is just you take a random number from 0 to 1 infinitely many times, right? And then limit of the expectation.
Yeah, okay. I think we need to meditate a bit, and let's continue next time. And I promise that I'll try to think about and write down the notes of what you said, and check what, and then discuss maybe before the seminar if I don't understand something, and then it will be somehow
okay.
And this proof is you invented this proof, or it's written somewhere, or what?
That's Martin's proof.
But
so
no. You read it in some paper, or you just invented?
It was twofold. So there was a summer school about these things.
Yeah, but it was completely ununderstandable. But you
I used two sources. That I used the video from the summer school.
Yeah.
In the paper of Martin, and some, as usually happens, you look at these things, you try to get an idea, and then.
So you cannot guarantee that this is identical to any of the existing proof, but probably it is.
It's of course it's like identical. How could I come up with something like this?
No, okay, but it's double negation argument, so okay. It cannot be different, but whether it's identical or not, it's not. Okay.
Is it linear combination of two?
Or maybe linear combination, or what? Okay, let's think
I
about
mean,
this.
I was thinking like maybe a bit. Maybe I was thinking a bit too much about myself, that I was able to like simply, you know, how you say it, like clean it up, right, and present it in a eatable, digestible
No,
form. But I guess I didn't do the job right.
No. I think actually, I think if you spoke in Russian, it will be better. But still, you will use obscene language, and it will be more clear and so on. But it's still okay. We should think a bit about this a bit, and I think we can reconstruct what you have said, and let's see.
You can reconstruct.
Huh?
You can reconstruct. Not all of us.
Okay, then next time we will start with the reconstruction. No, maybe I will fail, but I think that the plan is somehow clear, but for me, but I'm not sure it will work up to this point. Of course, another direction is not. But
in this step one, the only thing to be discussed is convergence theorem for supermartingales. The rest is rather clear.
Yeah. But maybe in this direction, it's always not needed. But just for definitely, we should understand whether convergence is true for supermartingales or not. And if it's stupid that we. No, it should be obvious. Maybe it's for me it's not, but after meditation it should be clear whether it's true or the argument works or not. But okay. Okay, so thanks a lot. And after so the next week we'll have this, and then we have some extraordinary seminar and at extraordinary time. Because we have a speaker from extraordinary place.
Yeah.
Andrei, can you say exactly what is the timing?
Let me try to find it.
12 o'clock Moscow time.
I think it was
no, 12:30, as I remember, the last.
We have shifted.
Yeah, 12:30.
Can you say it again? What will be? It will be Kolmogorov.
There we have an Australian or New Zealand guy,
Hong Kong
guy, about some information inequalities, very fresh.
He claims that some sort of statements about entropy, some class of problems about entropy is undecidable. And to prove it, he uses tilings.
Wow.
Undecidable, not in terms that they are independent from set theory, but just algorithmically.
Algorithmically. He embeds a question about the possibility to tile the plane into some statement about entropies.
Wow. Wow.
When it will linear inequalities or polynomial or even worse.
Monday, 3rd of December, I guess.
We will know.
Next Monday or not?
No, not next. Next by.
I think
on this seminar, but in like, you're right?
December 6th.
December 6th.
December 6th. Yes, December 6th.
So it's Kolmogorov-Seminar. It's another seminar.
Yeah, it's Kolmogorov-Seminar, but in an unusual time.
Okay, yeah.
Because a speaker is from Hong Kong.
Hong
Kong.
Our usual time is too late for him.
Okay, that's cool.
Okay, so also we can have something in our usual time, but probably it will be.
It's too much.
Yeah.
Yeah, but unfortunately I cannot be in at 12. But okay.
12:30.
12:30. That's worse. Well, I mean, I can be for 30 minutes, but
Yeah, but you are in Moscow. You are not in Hong Kong or Singapore.
no. I'm in Moscow.
Okay.
Okay. Next time I will not come, so you can speak in Russian, and then
And what will
I can
happen
read
with
the
you
notes
next
of
time?
Sasha.
But what will happen with you next time?
Oh no, but you say it will help in Russian, so it's
No.
important that-
Bruno, it will change a little because difficulty is not in
I mean, Sasha just insulted my English, but
I insulted Sasha in all possible ways.
Yeah.
Make him. If he
Okay,
spoke his
thanks,
Russian, I would say that his Russian is not good enough, and he should speak in English. So don't worry.
Okay. I think it's better if his
small-
English insulted than his Russian is insulted.
Yeah.
Okay.
This way, Kozachinsky has an excuse for talking so.
Okay, thanks.
Yeah. Your
I will
English
come.
is.
So I will come then next week.
Kolya's English is also not too good.
Yeah, I put in chat the title of that talk.
But Andrei, anyway, I'm looking forward for announcement to send.
Yeah, there will be an announcement and
The undecidability of conditional affine information inequality and conditional independence
inequalities.
application with a binary constraint. Yeah, it's something, yeah.
Sounds promising.
Yeah.
Okay, so I'm about to close.
I would just add 2 words at the end.
well, okay.
Satisfaction problem. And